Hello, this is Jonathan Wood from Soft Circuits. In this video, I'm going to provide an introduction to object-oriented programming. In short, object-oriented programming is a programming paradigm where code and data is organized into objects. Objects improve the modularity of your code and can make it easier to use and reuse that code. There are four generally accepted principles of object-oriented programming. They are encapsulation, abstraction, inheritance, and polymorphism. We'll cover each of these principles in more detail in a moment. But for now, encapsulation means to enclose code within an object. Abstraction is closely associated with encapsulation and means that the interface to the code within an object does not necessarily expose information about how that code is implemented. This can simplify the use of that code. Inheritance is where an object can easily be made to be a more specific or specialized type of another object. And polymorphism refers to having one of multiple methods execute from calling the same elements of an object's interface. C++ supports all of these principles of object-oriented programming, and MFC, for the most part, makes use of them. Anyway, that's quite a mouthful, so let's get down to some concrete examples. I'll create an MFC application that draws shapes in a window, and we'll use it to demonstrate some object-oriented principles. And I'll call the project Shapes. And we're just going to accept the default settings. So I'm going to add a class to our project. And I'm going to call the class C shape, and I'll put it in a file called shape.h and shape.cpp. And actually, for this, we want our destructor to be virtual. I'm going to make an inline class, and that simply means that there'll be no CPP class. Instead, everything is put in the header. That's not generally something I recommend for most classes, but for this demonstration, that'll make things a little easier. So we're going to demonstrate encapsulation here. We're going to have a couple of methods, and depending on your familiarity with C++ and classes, we do have a constructor that gets called when an instance of this class is created, and a destructor that's called when it is destroyed. And we're going to add a function or a method, and we'll go virtual draw, and we'll take a pointer to a device context. And we'll set it equals 0, which I'll explain in a second. And then I've created a CRect member, which is an MFC class, and I've made that protected. And this guarantees that no other code that uses this class will be accessing or modifying that member in any way. Now the draw method, I've done two things. First of all, I've made it virtual, and what that does is it allows us to use inheritance in another class, and if the other class derives from this one, which I will demonstrate later, then that other one will be called instead of this one, this version, and we'll demonstrate that later, like I say. And then also I've set that equals 0, and what that syntax means is that in C shape is not actually going to implement the draw method, and the result of that is C shape is called a pure virtual function, and you cannot create an instance of it because it's not fully implemented. We will simply use it to create other specialized classes or specialized shapes. Okay, so as demonstration of encapsulation then, we've organized a couple of routines and some data within a single class. We've hidden the m_rc to other code. And this example is pretty trivial, but it should be pretty easy to imagine how this type of organization and private members makes using code easier when it's encapsulated in a class. Okay, so now I'm going to try and demonstrate a little bit of abstraction, and I'll do that by adding another method called setRect, and it takes a couple of arguments that define a rectangle. And we will call on the m_rc method, we'll call the setRect method of that. And I'll create another one called offset, which will move the rectangle, and that'll just take two arguments telling how far to move the rectangle in either direction. And again, we're just going to transfer that over to the method of the rectangle, the crect object. So here we've made it appear as though these methods modify the shape directly, when they do so only indirectly by modifying this hidden member, data member. Again, this is pretty trivial, but this allows you to provide a very simple interface to much more complicated program logic. And in a larger program, this really can simplify what it is you need to do in order to use a class or object. Okay, so now we're going to demonstrate inheritance. And we're going to do that by creating specialized shapes, and they will inherit from the base class, the C-shape class we just created, which can only be inherited from. It can't be used any other way because we've set this a pure virtual function. So I'm going to go add class, and we're going to call this class C-circle. And instead of creating our own file for it, we're going to go ahead and put it in the same file, and we're going to specify C-shape as our base class. And that tells it how we're going to derive from that. And this will also be inline. And we get a warning that we're putting it in the same file that contains a class, which we want. And so here we can see the definition for our C-circle class, and it's followed by a colon and then C-shape and publics there, which tells us what happens to the methods of the C-shape, the members rather of the C-shape class. So now it's important to point out, when you inherit from a class, we automatically have the same methods that were in the other class. So here we have if you create an instance of the C-circle class, you automatically have a draw method, and you automatically have a setRect and an offset method, because that functionality is already there. It already contains all the functionality of the base class. And so what we're going to do now is we're going to override that draw method and give it an actual implementation. So again, it takes a pointer to a device context, which is a class MFC uses to draw, and we're simply going to call the ellipse method, and we pass the rectangle that we have in our base class. So again, we don't have to define that rectangle in the C-circle class. It's already defined in our base class. And I should point out that although that rectangle is protected, derived classes still have access to it. On the other hand, if I had declared it private instead of protected, then derived classes could not access it. So there we have a specialized shape class, a circle. And in fact, I'm going to copy that, and we'll call this one a square, and we have to change our constructor and destructor names, and we'll change our draw method to instead call rectangle. That takes the same arguments, and we're going to copy it one more time, and this one we'll call round square, which sounds like an oxymoron. Round square. And we'll implement our draw method, and we need a point that specifies the roundness of our corners. And then we'll call the round rect method of the device context. We pass it our rectangle, and we pass it our point that specifies how round our corners are. So again, we're demonstrating inheritance. We've made specialized versions of the shape type. By deriving from C-shape, these classes automatically assume all the functionality of the C-shape class in addition to any functionality they add or override. Okay, so now we're going to go to our view class, which the MFC wizards created for us. And I also want the header. And I'm going to include the shape header file that we just created so that all of our shapes are available to our view class. And we're going to create a collection of shapes. And so we'll add that to our view class definition. Normally it's not recommended to be adding data members to your view, but we'll keep this as simple as possible. So we're going to use a C array collection class that comes with MFC, and it's going to be of type shape pointer, and it'll take arguments of type shape pointer, and we'll call it m_shapes, and this creates a collection class that behaves like an array of C-shape pointers. Now we could also have made it just an array of C-shape objects and not pointers, but by having them pointers we have a little bit of more things we can do, which I'll demonstrate now. So on our constructor of our view, what we're going to do is we're going to create some shapes. So we'll do add and a new C circle, and we'll add a square, and we'll add round rect. And for good measure, we'll do it a couple times more. Now it's important to note that because we are storing pointers, the collection class is not able to clean up those pointers and erase the memory, free up the memory. So we need to take care of that in our destructor. So we can do this very easily now. We'll say int I equals 0 while I is less than the count of our array, and we will call delete, and we'll delete that member. Okay, now the next thing we want to do is initialize the position of our shapes. So we'll do that. And again, we're going to loop through all the members. And we're going to call that setRect method. And since it's a pointer, I need the pointer operator, setRect, and we'll give it the coordinates of the rectangle. And then so not everything's at the same location, we'll shift it each time. Now note that I'm calling that setRect, that's calling the base class for each of those methods, or each of those object types, but it's important to note that that works regardless of whether we're calling it on a circle or a square or a round square, which I've mistyped up here. And then we want to go ahead and draw those shapes on the screen. So we'll go to our Views on Draw method. We need the access to that device context, so we'll uncomment that. And we'll create a brush. And we'll make it green. And we'll select it into the device context and save the original brush, which we restore when we're done. Okay, and now here comes the fun part, to draw our shapes. And again, we're just going to loop through our collection. And now we're going to demonstrate the polymorphism. So we reference this particular shape, and remember, we don't know what the shape is. We don't know if it's a square or a circle or what. And yet we're calling the draw method, and remember the draw is different for each shape, and we pass the device context, and that's it. That's all we have to do to draw those. Again, using polymorphism, we were able to show, or rather call the same method without knowing what the object type is. So let's try to run that. And we have an error. We call offset rect is the method on the rectangle. Okay, and so there's all our different shapes drawn there. So again, that last bit demonstrated polymorphism. We called the draw method, for example, on each shape object in our collection, and it carries out the correct type of drawing for that particular object without us having to know which object we're referring to. And this makes the code very simple. And once again, you know, this is a trivial example, but tricks like these make object-oriented programming so useful in larger programs. And the thing you should really be getting from this is how once our objects are rather our classes are created, how easily it is to manipulate them and use them, and how simple our code is. And I'll do one more example of that. We'll test our offset method. So I'll go to our view, and add a, we'll just capture a click, the mouse click event for our view. There it is. And go to our messages. Go to our left button down. And again, we can do pretty simple code, loop through our collection. And we'll simply call that reference our each of those objects and call that offset. We'll just offset them each by 10 in both directions. And so, yeah, that's not working. Okay, I've just forgot to redraw the screen is all. So call invalidate after we change the objects. And I'll run that. And then you can see each time I click on the window, all those are moved and redrawn. And again, that happens with very little code. So hopefully what I've shown here is how object-oriented programming can be used to simplify some programming logic, and especially for larger programs, it's yet another tool for organizing your code and making things a little better or a little easier to work on.